Alright guys, in the last video we covered off the basic mechanics of ACL injury, and one of the things that we noticed across multiple study types is this multiplanar loading mechanism. Now multiplanar loading is exactly what it sounds like. It's basically talking about loading, in this case of the knee joint, across its multiple planes. So in this case we're talking about the sagittal, frontal and transverse plane. Now in the sagittal plane the evidence is very clear, and anterior shear force will tend to load the ACL, posterior shear force will tend to unload the ACL. If you remember back to the basic functional anatomy of the ACL in the earlier video, basically we learned that the ACL resists anterior translation of the tibia. Therefore, if you apply an anterior shear force to the tibia, you're obviously going to strain the ACL. Now in the frontal plane, the main loading type we talked about was knee valgus loading. And again, the evidence is relatively clear that if you apply a knee valgus load to the knee, that will increase loading on the ACL. Interestingly, if you look at all the evidence, knee varus loading actually also tends to increase load on the ACL to a pretty equal extent compared to knee valgus loading. However, in the real world, we very rarely observe knee varus occurring during ACL injuries, and that just has to do with the practicalities of how you move. So as a consequence, we tend to focus more on knee valgus loading as the thing that we try to avoid to protect our ACLs. In the transverse plane, the evidence suggests that external rotation will tend to load the ACL, but also that internal rotation loads the ACL, and it tends to load the ACL to a far greater extent than external rotation. So basically, if you combine these different loading types, so anterior shear force, knee valgus, and then either external or internal rotation, that's really when your ACL is particularly vulnerable. Now, one other loading type which I haven't spoken about yet is compression. And the reason I haven't spoken about it in any great detail is because the evidence behind it is actually a little bit contentious. Some literature points to the fact that compression at the knee is actually a good thing, because obviously if you compress two bones against each other, it makes it harder to induce something like anterior tibial translation or posterior translation, because you're essentially squeezing the two bones together. So that's why compression might actually be a good thing. But there's also evidence that compression can be a bad thing, mainly because the top of the tibia, what we call the tibial plateau, it actually slopes posteriorly slightly. So if you apply a compressive force on it, it actually tends to push the tibia forward slightly, which would put stress on the ACL and potentially cause some problems. So for that reason, we're not really going to worry too much about compression for the sake of this video series. But just note that multiplanar loading mechanism is really important. And as a consequence, we are interested in where these loads actually really come from. And one of the predominant sources of these loads actually comes from within the body, and it actually comes from muscles. So in this slide, I'm going to try and give you an explanation as to how muscles can contribute to joint loads. And hopefully this will be a relatively simple example. And then in the next slide, I'll talk about a little bit more of the complicated stuff. So to start off with, just a reminder that obviously if the tibia moves forwards relative to the femur, that would be when the ACL is loaded. So that's something we're typically trying to avoid. So to give you an explanation as to how muscles can induce these loads, we're just going to focus on some pretty basic muscles that cross the knee. In this case, I've got the quadriceps towards the front and then the hamstrings at the back. Now, if you recognize that these are muscles and they can produce force, if you look at the way in which the muscle attaches to the tibia and the way it crosses the knee, that actually influences how each muscle will actually induce a joint load. So for the quadriceps, the force vector would look something like this. And then for the hamstrings, the force vector would look something like this. Now, because these are force vectors, we can break them down into their orthogonal components. The first component is the compressive component, and in both cases, for both the quads and the hamstrings, they tend to induce joint compression. So they basically pull the tibia into the femur, or they squeeze them together. Now remember, this might be a good thing, this might be a bad thing, we don't really know. But if you look at the shear component, it becomes a lot more clear. So if you look at the shear component, it seems that the quadriceps tend to pull the tibia anteriorly, which remember, that's going to stress the ACL, whereas the hamstrings pull the tibia posteriorly, and remember, that's going to unload the ACL. So if you remember back to one of my previous videos, I mentioned that from cadaveric studies, we found that increasing quadriceps force tends to increase ACL loading. Well, based on this, we can actually see that that is because the quadriceps tend to pull the tibia forwards. We also mentioned that the hamstrings, if we increase force in the hamstrings, it tends to unload the ACL. Well, you can see here, that's because the hamstrings tend to pull the tibia backwards. Now, based on this diagram, what we're really learning is that the way in which the muscle attaches to various bones, or the way in which it crosses a joint, is critical in determining how it induces joint loads. However, it's actually possible for muscles that don't cross the knee to actually induce knee joint loads. And this is going to be more complicated to explain because I'm going to have to refer to a concept called dynamic coupling. Because it's so complicated, I'm going to try and simplify it and just focus on one example. And I'm going to talk about an example. Imagine someone walking, as you can see in this diagram on the left-hand side. Now, I'll just focus on one muscle, and in this case, it's going to be the soleus, which is one of your muscles in your calf. I'll focus on the soleus because it's a pretty strong muscle, so therefore it tends to get some attention. And it's also a very simple muscle to understand because it really only has one action, and in this case, it's ankle plantar flexion. Now, if the foot is free in space and the muscle contracts, in this case the soleus, it will induce ankle plantar flexion, which would look like this. Now, the key thing I want you to notice is that when ankle plantar flexion occurs, what's really happening is that the top of the foot is getting further away from the front of the tibia. Okay, so you can clearly see that in this example. Now, at some points of the walking cycle, obviously your foot's going to be in contact with the ground, okay? So if your foot's in contact with the ground, so now I've got a ground underneath the foot, when the soleus contracts, it's still going to try and induce plantar flexion, which remember is pulling the top of the foot away from the front of the tibia, except it's not going to be able to move down, right? It's going to try to move down, but instead the foot's going to be in contact with the ground. And for every action, there's an equal and opposite reaction. So the ground's going to exert a reaction force back up against the foot. And that reaction force will actually continue to propagate up the skeletal chain for that same reason, right? And every action, equal and opposite reaction. Now remember, what the soleus is really trying to do is pull the front of the tibia away from the top of the foot. So it's actually going to pull the tibia backwards. And because the tibia is linked to the femur at the knee joint, it's actually going to result in knee extension. So if you look up the action of the soleus in any anatomy textbook, they'll all list ankle plantar flexion as one of its main actions, and yet none of them will list a soleus action as knee extension, but clearly in this example, the soleus can actually contribute to knee extension. Now, dynamic coupling is very complicated. It's dependent on the attachment points of the muscle, and it's also dependent on the kinematics of the entire body. So it's very difficult to predict. It probably changes from task to task. So the soleus will always induce ankle plantar flexion because of the way it crosses the ankle joint, but its action at the knee and the hip and any other joint in the body will actually change depending on the position of the entire body. So the only way we can really understand the dynamic coupling of a muscle is to analyze it in a task-specific way. And as you know from the previous sections of these videos, ACL injuries often occurs during tasks like single leg landing and sidestep cutting. So what I wanted to do, knowing that non-knee spanning muscles could actually induce knee joint loading, is I wanted to work out how these muscles would actually induce knee joint loads during a relevant ACL injury mechanism like sidestep cutting. And this was one of the major studies in my PhD, and this one's already been published. So basically what I did here was I did some 3D motion analysis. So I got a bunch of people to do some sidestep cutting in the lab. I got their 3D joint angles. I also had them do the cutting on a force plate. And then using the motion data and the force data, I was able to calculate joint moments and then eventually get into some estimations of muscle forces and then basically calculate how muscles were contributing to joint loading. Now, the nitty-gritty details of that is beyond the scope of this presentation. You don't need to know them. But essentially what I eventually came up with is the data where I was able to work out how muscles contribute to knee joint loads in the sagittal, frontal, and transverse plane. And really I was focused on the muscles that could oppose ACL loading. Okay, so these are the muscles that we could potentially target to protect the ACL. Now in the sagittal plane, what I found is that the main muscles that could induce a posterior shear force, so remember that would unload the ACL, was the biceps femoris long head, the medial hamstrings, and the soleus. Now, obviously, the biceps femoris long head and the medial hamstrings together make up the hamstring muscle group. So that's very consistent with the previous evidence that I've shown you. The soleus, I found, was also a really important muscle to inducing posterior shear force, even though it doesn't cross the knee. Now, these same muscles also induced frontal plane loading, and what I found is that the biceps femoris long head and the soleus actually tended to contribute to knee valgus loading, which probably isn't a good thing, but that was somewhat opposed by the medial hamstrings. And what was really interesting, in my opinion, is that the dominant muscles for opposing knee valgus loading were actually the glute max and the glute medius, despite the fact that they don't actually cross the knee joint. Now, these muscles together were also the main muscles that induced loading in the transverse plane, and they tended to pretty much oppose each other. So if you take all of this evidence together, if you can find a way to enhance the recruitment of the hamstrings, the soleus, and also the glute medius and maximus, then potentially it might be happy days for the ACL. Now, one limitation, and well, there's plenty of limitations with all research, but for this particular study that I did, there are some pretty important limitations that you should be aware of. And the first is, this is really just providing a theoretical or biomechanical framework for interventions that aim to reduce injury risk, but the study itself did not actually quantify risk. So it's not like I enhanced the activation of these muscles and then everyone who did that had a lower incidence of ACL injury. There was nothing like that. It was just a cross-sectional study, got a bunch of athletes in, tested them, worked out the actions of the muscles. So all this really tells us is that theoretically, if we can find a way to enhance the force production in these muscles during a sidestep cut, then it could potentially protect the ACL. So it's basically providing some indirect evidence that if we can find a way to enhance these muscles' force production during a sidestep cut, it might protect the ACL. And I really want you guys to keep that in mind in the next video when we start talking about interventions, because this is an example of indirect evidence, but we do actually have some direct evidence that informs our interventions in terms of reducing our risk of ACL injury.